Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2024 VCE Northern Hemisphere Maths Methods Exam 2 of the extended response questions. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. So basically these are suggested solutions. Just a disclaimer, these are my suggested solutions. Vika hasn't posted any solutions, so I just wanted to make my own suggested solutions. And yeah, if you see a basic mistake, you see a simple mistake, let me know. I'll try to fix it. And I'm going to try to be as detailed as I can in my answering, and I'll try to explain it very simply, because I think I want to try to help as many students as I can, that those who struggle with methods, when they watch this video, they can understand step by step how to do the question. So it is going to take a very long time, but I'm going to try to be as much detailed as I can just to help as many students. And yeah guys, I hope you guys enjoyed this video, and yeah, let's smash through it. So question 1, consider the function f. So the domain is all reals. F of x is this, so x cubed minus px, where p is an element of all reals. Part of the graph of f is shown when p equals 3. Beautiful. Find the values, so there's many values, of the x-intercepts of f when p equals 3. Beautiful. So let's actually define this in our CAS. So f of x is going to be defined as x to the power of 3 minus p times x. Now, it's saying p is 3 for this case, so we're going to put p equals 3. And so we just need to find the x-intercepts. And to find the x-intercepts, you just let f of x equals 0, and you solve for x's. So solve, answer, comma, x. And we get 3 here. So beautiful. Let's write these 3 down. So x is equal to negative root 3, x equals 0, and x equals root 3. Beautiful. Those are the answers for the first part. Nice. Sorry, my chair's making so much noise. B. Use the derivative of f dash to find the coordinates of the turning point of f when p equals 3. Beautiful. So it is 2 marks. So what you want to show is, if we want to find the turning points, of course we want to find the derivative of f, so which is f dash of x. And you can do that by hand, basically. It's quite easy. Remember, this case is where f is 3. Where p is 3, my apologies. So x to the power of 3 minus 3x. So let's find the derivative of this. 3x squared minus 3. And basically we solve it. To find turning points, we solve where f dash of x equals 0. And let's do that all in our CAS right now. So what we want to do is basically solve where basically we derive f of x, which is what we have, and we want to let it equal to 0, comma, x. And these are the values where our stationary points are, or our turning points. But remember, we want to find the coordinates. So we want to also find their y values. So for f of negative 1, it's this, and f of 1 is this. Beautiful. So let's write that down. So we know that basically negative 1, the coordinate of a y coordinate is 2, and 1, and the y coordinate is negative 2. So what the first mark will come actually finding the derivative, and then basically getting those coordinates is the second mark. Beautiful. So this is what you need. All right, looks all good, no mistake, looks nice. Next question. Let's have a try at this. So find the value, so it's only one value, just from the word, of p for which f would have exactly 1 stationary point. One stationary point. Well, let's think about it. Let's go back to the original function. So to find stationary points, we find the derivative, don't we? So when we find stationary points, we normally find the derivative. So which is 3x squared in this case, minus p. And so when the solutions that we get from these equations when we solve it equaling to 0 is the number of stationary points. So if we basically want to find out, we want to have exactly 1 stationary point, basically we only want 1 solution, not 2 solutions or no solutions, just 1. And remember, it is a quadratic. Have a look at it. This is a quadratic expression. So what does this remind you of? So let me write it nicely. So imagine that's a plus 0x minus p. This should remind you of the discriminant. Because we want to find 1 solution, so basically the solutions to these are stationary points. Because we want to find 1 stationary point, we want only the discriminant to be equal to 0. which will give us one solution. So let's do that. So remember the discriminant is b squared minus 4ac. So our b squared in this case is what? It's 0 squared, which is just 0, minus 4, our a is 3, and our c is negative p, must be equal to 0, which is basically 12p equals 0, so divide both sides by p is going to be equal to 0. So when p equals 0, we have one stationary point. And let's actually check that. So imagine you sub in p in here. You'll actually get rid of this thing, and you'll be left with a cubic, x to the power of 3. And we know x to the power of 3, we know it's just a cubic that has a point of inflection, a stationary point of inflection. And it's only one stationary point. So this is beautiful. So it does make sense. So that is your answer. And it's, you remember, the question said 1. So, find the value. So there's only one answer. So only p equals 0 for that one. I hope that makes sense. So find the value. We're going to say p equals 0. Okay. I'm going to highlight that. So beautiful. I'm just going to leave that there right now. Okay, next question. Find the values. So there's many values now of p, which f would have no stationary points. Easy. This is when the discriminant is less than 0. Remember, so we want no solutions for this. So it's basically the same formula. So imagine the same formula, but now it's going to be this has to be less than 0. So meaning that basically this here changes inequality to less than 0. And so if we divide both sides, of course, by 12, you get basically still p is less than 0. So this here is where we will get no stationary points. And yeah, so let's check that. I don't always just double check it. So let's graph it and let's double check if that makes sense. So so when p is less than 0, we should get a no stationary point. So let's go to our CAS and let's graph the graph. So x to the power of 3 minus p times x. Enter. So we've got this graph here. And so if p, let's say it's like, negative 10, and this is 0. So the values between negative 10, like 0 to negative infinity, that's what it was saying, is you can see that there's actually no point of inflection. Like when it's at 0, basically, of course, when it's at 0, there is a point of inflection, but that's when you go, because we're saying p is less than 0, not equal to 0. After we go less than that, this is not a point of inflection, so it is a point of inflection, but it's not a stationary point, of inflection. So, because if you draw a tangent, it's not stationary. It's not a horizontal line, that tangent at x equals 0. So, I hope that makes sense. So, when p is basically less than 0, we basically get this kind of graph, which has no stationary points. So, yeah, where p is less than 0. That's your answer for the next one. So, I'm going to write it in this notation, much more easier. So, p is an element from negative infinity to 0, not including 0. Remember, if you include 0, you do that's when basically you do have one stationary point. Okay, beautiful. Next question. The graph of f passes through the origin for all values of p. Use calculus to show that the tangent to f at the origin has this equation. That's easy. Let's do that. So first I want to understand. It says the graph of f passes through the origin for all values of p. I really want to check that. So let's go back to our CAS. Say this is like, I don't know, 10. So can you see when any value of p, saying all values of p, yes, it's always on the origin, you can see. Yeah. As many times as you want p, it's always going to have that origin there. As many values of p you want to put, yeah, it's always going to pass through the origin. And what we want to basically do is find the tangent line, the equation of the tangent. It is a show question, so leave your CAS and let's do it by hand. All right. So what we need to find the tangent is we need a point on that tangent, a point. So let's have a look here. So this is like the, representation of the line. It's like a cross up, like, they basically, when we were playing with p, it looked like around this. All the shapes look like this. So if we wanted a tangent, so if I draw like a nice tangent at x equals 0, I mean, it's not the most nicest, but it does kind of, it's like, yeah, just think of it like that. So that's the tangent, yeah? So we need for to find the equation of a tangent, we need a point. And luckily we do have a point. Remember 0, 0. That's the origin. So it passes through the origin and we need to find the gradient. And how do we find that gradient? Easy. We find the gradient by using the derivative function. Because remember, it is a tangent at 0. So let's do that. So first of all, what is f dash of x? So f dash of x basically is 3x squared. 3x squared minus p. Is that right? Yep. So subbing in 0, you get negative p. So this here is your gradient. That negative p is our gradient, m. So we've got our gradient, and we know it passes through 0, 0, which is that point. So using our y2 minus y1 equals m times, so y2, so what am I saying y2? So like y minus y1 equals m x minus x1, so which is the equation of a tangent. We sub those all in, so y minus, what's your y value? It's 0. What's your gradient? It's negative p, we found out. And x minus 0, basically. So subbing all this in, we get negative px. Aha, we have proved that the equation of that tangent is given by this formula. Beautiful. That is it for that one. And yeah, it makes sense. Beautiful. So, next question. So, find in terms of P, the area of the region bounded by the function f, the line y equals negative px, and the line x equals p, where p is greater than 0. So, p has to be greater than 0. Now, let's visualize this. So, let's actually go on our calculator and just graph what we basically, all the equations, and see what area are we trying to find out. So let's do that. So let's go back to our CAS. Okay, so we've got x cubed to the negative px. That's our function f. We also have to draw that negative p times x. Sorry, negative p times x equation. And we also have to draw that x equals p line, we said. So go graph, relations x equals p. Beautiful. Let me move these out. So if you remember, and p is, what did they say? P is greater than 0. So 0 is the lowest point. And something like 0 to 10, let's say. So if I play around this, you can see that the area that's bounded, that's what we want, is here. So if I move, increase, so what's happening? Still the same, just increases. More, it just increases, so let's just make it a little bit smaller, 0 to 2. So if I put any p-value, you can see it's just increasing. It's that area is just increasing, the bounded area. Just increase. And it's just the same. It's always the top function is your f of x, and your bottom function is that tangent line, which is negative px. And just increase, it's just the same thing, and that's x equals p. So beautiful. So we kind of know and visualize it like in a very visual way. So let's kind of graph it on our page, and let's see what we can get from that. Let's go. So if I graph this on my kind of visually here, so we basically have this, the equation f of x that looks basically like this. Beautiful. And if we draw a tangent, that tangent, which basically moves like that, this tangent, and so that's your basically negative p of x. That's this one here, the yellow one's f of x. And the line, always x equals p, it's like around here. So it forms this, so sorry, this is like, yeah, it's that shaded region here. Okay, and so that's at x equals p. So what's the general formula? Because we want to find the area in terms of the region. So we want to basically write an integral. Easy. So the integral is going to be what? Remember, where are we going to start? So from here, because we want to find this area under here. So it's always from 0 to the value of p. From 0 to p. So from 0 to p, what's your top function? Now, normally from all we were playing around, we always saw that f of x was greater. It was always the top function, greater than, negative p of x. So it's going to be f of x minus your bottom function, which is negative p of x, dx. And so this formula should give us our actual equation, in terms of p of the area. So I'm going to move this to the side now, and let's use our CAS to simplify this. So basically, this here should give you 1 mark, this expression right here. Okay. Equals what? So let's write that down. Okay. So because I don't want to make any mistakes, I'm just going to basically redefine the function to another problem. So I'm going to just copy this, Control up, insert problem. There it is. And that was p. Yep, let's just go back. I want to just double check. Yep, so x cubed minus p of x. Beautiful. And so now we said it was the integral from 0 to p, f of x minus p of x, p times x. dx. That gives me p to the power 4 over 4. So that's our area. Let's put that there. So p to the power of 4 over 4. That is my answer. Beautiful. Let's highlight that. Next question. Let's have a try at the next question. All right. The expression for the area found in part dii, so this one here, also gives the area bounded by this cubic function. So y equals k times x to the power 3. So it's just a cubic function where k is just like a constant. The x-axis and the line x equals p, where p is always greater than 0. Find all possible values of k. All right. So let's have a try at this. Let's delete this. Let's have a try. So it's a cubic function. So if I draw a cubic function, now that's two cases of a cubic function. This could be. Let's think about it. We can have where k is greater than 0. So k is a positive number. And we know a cubic is going to look like this. Like that. Yep. So if k is like, 2, 3, 4, any positive number, it's going to look like that. And if k is less than 0, so a negative number, there could be a possibility of this here. So we have two possibilities. It could be like this. And so this is the area here. Now, we know p is greater than 0. So if we draw like a line, just a straight line, for example, for this one here, we'll draw a straight line here. That's x equals p. So the same for here. X equals p. Beautiful. So the expression for the area found in also gives the area bounded for the cubic function, the x-axis, and the line x equals p, where it's p is greater than 0. And so this here, so basically it's telling you that this formula over here, this expression gives us these areas, this area and this area over here. Now let's look at the first case, because it says find the value, so there's actually many values. Let's try the first case. So let's write an expression for the area under this graph here, the first one, this here. So it's basically going to be, of course, from 0 to p of, kx squared, so x cubed, dx, must be equal to your actual equation. So that p to the power of 4, because that's expression. It's because it's gives the area bounded. Done. And so that's one equation. That's one possible source of solution that we can get. The other source of equation, remember, where it's when x is less than 0. Because remember, this here is giving you the area. Yeah, even though this area, it's at the bottom, like it's, negative, we're talking about area. So we always have to make sure it's positive. So how would we write this? Oops. We would write this as from 0 to p, and put a negative in front of it, because remember, this is going to be negative area. And we want to make sure it's positive, because area is always positive, of this equation. So kx cubed dx must be also equal to p to the power of 4 over 4. That's your second equation. So you can see that there's two possibilities. And now we can actually solve these two and find what k value should be. So let's do that. I'm going to kind of delete these now. There's no need for these. So we just needed to find that there was two possibilities. And so let's put this down here. So let's try the first one on our CAS, and we'll put both of them. So the first one was the integral from 0 to p, k times x to the power of 3 dx equals p to the power of 4 over 4. And so when we solve this, answer comma k, we get k equals 1. Beautiful, that's one of them. And what about the next case? Remember, with this, but there's a negative in front of it. And it should be basically like the opposite. So solve answer comma k. K equals -1. So these are your two possibilities of k that we can get. Beautiful. So let's write those down. So k equals 1 and k equals -1. Beautiful. They're kind of giving you the hint, because it's saying find all possible values of k. I hope that makes sense. So that is question 1 done. I'm quite actually happy. So let me just put that over done. Not too bad of a question, I'm not going to lie. Quite fun. Okay, question 2. Let's smash through this paper, this one here. Question 2. So a simple pendulum consists of a mass at the end of the string. So we can see this mass over here, right over here. And it's at this end of the string. We have a string, and at the end of it, it has a mass. Beautiful. That is a fixed length of 0.5 meters. So the length of this string is actually 0.5. So the length of it the string here is 0.5 meters. So just know that. The other end of the string is attached to the fixed point O. So this end of it is fixed at the point O. Beautiful. The mass swings back and forth in a circular arc between point A and C, and each time passing through B. Easy. So you can see it's like a pendulum. So it goes like that. Oscillates between A and B is the halfway value, which is always passing through it. Now, let's have a try at this. The height h of the mass above the horizontal floor. All right, so h is that. So this is the floor. It's the height above it, basically. So it's always where the mass is, and it's always the height. So if the mass was here, it's this height over here. If the mass was here, it's this height over here. So it tells you the mass above the ground. Just know that. All right. So, okay, we've given the kind of function. So it's saying h is, okay, so it gives us the height, but it gives it in terms of theta, where theta is the angle you can see from the mean. So from B, basically. If theta is positive, it means it's going to the right. If theta is negative, it's going this way, basically. And of course, we can. They've also given us the, the maximum values of thetas that we can go. Basically, meaning that, of course, it makes sense. Like A is the maximum angle we can go. Like from this position to this angle here, it should be pi on 3. And then when it goes this way, which is negative pi on 3, these are the maximum values. These are the maximum angles that we can go when it's oscillating. It can go greater than those. Hope that makes sense. Not too bad. So just understanding that slowly. All right. Next question. Let's look at this part. So where theta is the angle, yep, in radians. So in radians, measured anti-clockwise from the vertical OB. Yep, so as we said, it is in the anti-clockwise. The mass reaches its maximum height at point A, which is theta pi on 3, and at point C when theta is negative pi on 3, and reaches a minimum height at point B with theta 0. Easy, makes sense. You can see that at A and B, they should be the same height values. You can see, because of the symmetrical properties, this here, these are your maximum heights. These are the heights that would, in which it's the greatest. Whereas B, of course, it's the smallest height. You can see this height here, it's quite small. It's the lowest height. All right, now, so A, find the maximum and minimum heights of the mass in meters above the ground. Easy. Well, we're trying to look at okay, let's look at the maximum height. Didn't we say that the maximum height basically occurs at any of these values? So it can be at A or C. They have the same maximum height because of symmetrical properties. Yep. So we can see that this is, you remember how they just told you right now that this is the maximum height? The maximum height occurs when it's at A and C. Yep. So, and how do we find that height? Quite easy. Well, we know the angle from the angle to, let's say, in this case, just A. So it's from 0 A, it's pi on 3. You sub in basically, so h of pi on 3, that here should give you the height above the ground. It'll give you this height. Easy. And it should be the same, because C has to have the same, because it's also the maximum. It should also be the same when you sub in negative pi on 3. So this is negative pi on 3 here. Go on the other side. So you sub in h equals negative pi on 3. So h of negative pi on 3. It should also give you the same height value. Hope that makes sense. So that's the maximum. So let's just write that nicely. So max is given by h on pi on 3. I'm writing h pi on 3. You can write h of negative pi on 3, still will give you the same answer. And so we'll do that in the cats. But first, also, let's do the minimum. So remember, the minimum occurs, the lowest height, the smallest height is, remember, they told you it is at B. So B. And what is the angle at B? It's 0. See, it's 0. It doesn't, it's straight. It's actually parallel. It doesn't move. So it's 0. So it's basically h of 0. Angle. And so these two, let's do them and let's find out what they are. So I'm just gonna control N and define all the stuff, the new stuff. Sorry. All right, so let's define the function h of theta. So I don't have theta, I'm gonna write x. So x is the angle. So imagine x is our angle for this question. So let's write it. It's 3 on 2, the equation. Always define the equation. Minus half times cosine x, basically. Done. So we wanted to find what's h on pi on 3 and h of 0. So this is your max height. This is your minimum height. Let's write down. So 5 on 4 meters, and the other one was 1 meter. Beautiful. These are your values. Okay, next question. Find correct to 2 decimal places the values of theta for which the mass has a height of h less than 1.1 meter. So the height is less than 1.1 meters. Let's think about that. So if the mass is at point B, which is the lowest, the lowest height, is at 1 meter. We found that the lowest, this distance from here is 1 meter. So we want to, basically, we know like if it increases, the height increases. Let's say this here is where 1.1 is. The height is 1.1. Let's say that is where 1.1 is. And because of symmetrical properties, this also would be the same distance. This also would be, but it will be negative, the angle. Also the same height. So we can see like if we drew like a line, basically, a nice line, straight line, and say this here, and say this is 1.1 meters. We can see what angles are possible, what angles basically give you these possibilities, where basically, so the values of theta for which the mass has a height less than 1.1. So say if that was 1.1, it means these are the values here that are less than 1.1. The height is less than 1.1. Yep. So this is where it's less than 1.1. And we want to find the values of theta. Well, that's quite easy because we can know that theta is going to be basically, when is theta? What's the angle? We just need to find its angle. What is theta when the height is at 1.1? And let's say it's a number. Let's say it's like 2, 2 degrees. Let's just make it up right now. 2 degrees. So let's say this was 2 degrees. By symmetry, this also has to be, 2 degrees. Also, but it's going to be negative, basically. Negative 2 degrees because it's in the, clockwise direction. And so basically, if you were trying to find the range, you would say theta is between, can they be equal, actually? Let's just check. So corrected with the values for which the mass has a less than 1.1, not equal. Be careful. Less than. So they cannot be equal to that. So theta will be between -2 to 2. These are the angles. So basically, if theta is between any part here, then the height is going to be less than 1.1. But if they are equal, like if the angle is between -2 and greater, it's going to be greater than or equal to 1.1. I hope that makes sense. So let's do this by what we just said. So we need to find that theta. Now we just need to find the theta for 1, actually. So in this case, let's find the theta when the height has to be 1.1 here, this height here. And this will give us the angle, this theta here. So let's go to our CAS. Let's do that. So theta x equals 1.1, and we will solve answer comma x. And of course, x is restricted. It is restricted from, because it's an angle, from what was it? Sorry, it said negative pi on 3. Negative pi on 3 less or equal x pi on 3. Beautiful. And there it is. We get 2 values. It makes sense. And you can see that they are symmetrical. And these are your actual, in radians, these are your angles. So let's come back to our paper. So basically this lets me know that this angle here is 0.6435 approximately. And also, because it's 1.1. And remember also this is 1.1 by symmetry. So this one here is, like we said, it will be just a negative angle of this, which we found out was negative 0.64. And yeah, that is the range of values. So when the values are between these 2 values, this is where, the height is less than 1.1. So let's write that down. I did not show any working out, but let's just write the answer first. So theta is less than, we said, so the maximum value was 0.62. How many decimal places? 2 decimal places, so 6.4. And the other one's going to be negative 0.64 because of symmetry. Beautiful. So that's your answer. And remember, make sure they are not equal because we want it to be less than. And so we get this. Beautiful. So how do we get our answer? Well, we just need to show some working out. Like, for example, when we said that h of theta equals, when we solved for h of theta when it's 1.1, we found that the thetas were both negative 0.64 and x, so theta must be equal to 0.64. Now, I think you'll basically get the mark, just these 2 marks from the answer and also stating this, solving these values of theta here. I hope that makes sense. So this is actually a nice question, not too bad. So yeah, I hope I haven't made any mistake in this one. Beautiful. Looks good. Next question. Question C. The angle theta radians as a function of time, seconds, is given by this function. All right. So this is the angle. Now this is the angle versus time. So in 1 second, what's the angle? All right. So this is the function for it, where it's between 0 and 30. All right. So the time is between 0 to 30 seconds. Show that the mass is initially at point A. Let's do that. So if we want to show it, so let's sub in on this function where t equals 0, that's initially, when t equals, initially that's when t equals 0. And so what's the angle? So if you solve the angle, so pi on 3, cosine 0, and we know cosine 0 is what? Cosine 0 is 1. It's pi on 3. And what do we know about pi on 3? Come back here. What did I say? When angle is pi on 3, it's the maximum height at point A, like we said. I'm so sorry, this is a lot of mess, so let me just take it out, rub this out. So remember, we said that this angle here is pi on 3. It's at point A. So yeah, it is at point A. So we showed basically that theta, when it's 0, it's pi on 3. The angle, so the angle tells us that the mass is at point A, So yeah, the angle tells us that the mass is at point A. Beautiful. Oh, there's only 1 mark, so you just had to show that. D, let's have a try at this one. Determine the period of the pendulum. The period is the time in seconds taken for the mass to travel from A to C and back to A. So let's think about that. So it's the time taken to go from, so here's A, it goes from A to C, so the whole distance from A to C, and then back to A. All right, that's not too bad, because if we kind of graph this, the theta over time graph, let's think about it. If I graph only like a section of it, we don't want to draw a crazy, only a section of it. So if I graph the graph of this, and it probably looks like, this. Yep, it looks like that, basically, like this. Something like that. And, and it goes forever, by the way, but from 0 to 30. But, so we know this here, this is the maximum value, pi on 3, and this is the lowest maximum, which is negative pi on 3. Remember, it starts at pi on 3, meaning it's right now at A. And pi on 3 is what? It's C. So think about it. The mass is initially at pi on 3, yeah? And so it, goes basically from A and just goes to C. And remember, C is when it's at negative, the angle is negative pi on 3. So basically, it's at A and it goes down to the angle negative pi on 3, which now it is at C. And so remember, it goes from C and back to A. So it goes back to the maximum value, which is pi on 3. And what does this tell us? Remember the period, it's the time taken to reach that. And isn't it just basically the period of the function? It's just the time it takes for a complete cycle of this function. That's what it is. So now we can actually do, it's just the period of this function. So basically just period is 2 pi divided by, what's the period of this function? 9 over 2, which is basically, we can write it as 2 on 9. That's when you divide them, which is 4 pi on 9 seconds. Beautiful. That's not too bad. Next question. How many times for t is from t equals 0 to 30 is the mass at point A? So we know that when it's every time at the maximum value, so this here, at the maximum value, that's where it's point A, point A, point A. So if we graph this function from 0 to 30 and count how many maximums there are, this tells us that where it was at point A. So let's do that. Okay, let's go back to our CAS and let's, graph it, of course. So I'm going to actually define it. I'm going to call it, because how our angle is known as x, I'm going to call it x of t is pi on 3 times cosine 9 times t divided by 2. Beautiful. So graph this. Ooh, that's a little bit struggle. Let me copy that. Because when you draw it will be X on X and stuff. Just take it. Let's just graph it here. And just make sure it's... Oh, no. Yeah, can you see how we define X? So we don't want to mess around with this. Just copy this right now. And let's make a new problem. And let's have a graph up there. New problem. All right. Graph. This one. X. And we want the domain to be 0 to 30. Okay. There it is. And so we have to calculate count how many maximums there are. So, wow, there's a lot. Wow, there's actually quite a lot. So these are what it is. So let's count them. I don't know why would they do this, but that's the first maximum. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there's 22 maximums. So basically, if it's 22 maximums, it's at 0.8. The maximum value basically is A. So let's put that, how many times for 0 to 30 is the mass at 0.8? It is 22 times. Done. So that's beautiful. Next part. Determine the distance in meters that the mass travels as it swings from point A to point C. All right, let's go here. So we're saying we want to determine the distance if it's going from A to C. A to C. So like this distance here. Well, if you actually think about it, wait. If we know the angle here to here is pi on 3, yeah, which is basically 60 degrees. Which is 60 degrees. And we know also this is 60 degrees. That is 120 overall. The angle here is 120. If you know this, look at this. This is actually good. This question's nice. If you look at a circle, yeah, a total circle, we know that isn't 120 1/3 of a circle? For example, if I split this, one straight horizontal, not the most nicest, but one like this. So if I draw it as 1/3, we know because the total angle is 360 in a circle. So imagine dividing that by 3. So this has to be 120, this has to be 120, and that has to be 120. So imagine here, this is what we are focused on, 120. Yep. Isn't that quite now? That's what this case is. You can see. That's 120. Imagine that part section is this section of the, this. So, how is this very helpful? Well, remember we have a circle, and we want to find basically this distance here, which is what we want as it travels from here to here. That's quite easy because remember, we know that a full circumference of the circle, the whole distance around it, is known as the circumference. So it's C equals 2 pi r. Now, we only want 1/3 of it. We don't want these extra 2. We only want one part of it, that third. So we divide it by 3. Just divide it by 3. And now that's going to give you that distance. Easy. And also one important thing, what is the radius? Well, what's this radius? That's actually, they told us it was 1.5, 0.5? Yeah, 0.5, the length of the string. So that is your formula. So, hope that makes sense. So 2 pi r over 3. So let's write that down. D is 2 pi r over 3, where the radius is 0.5, if I'm not mistaken, over 3. Let's just double check that. Was it 0.5? Yep, it is. So it's like half times 2, which is just pi on 3 overall. Pi on 3. That's it. That is the distance that it travels. Beautiful. Not too bad. Okay. That's it. Is that? Oh, we have more of the question. Wow. G. Find corrected 2 decimal places the height of the mass in meters after 1 second has elapsed. Easy. So, we basically, to calculate the height, we have the height formula. But the height formula is in terms of the angle theta. So, yeah, height of theta. We have this, which gives us the height at any angle. So, we need the angle. But easy. We know the angle. We have the angle versus time graph. So which we can basically, if we want 1 second, so after 1 second, what's the angle? So we put it in this formula. So to find the angle, theta is 1 second. We're using this here. It's going to give me the angle. And so now I have that. I could sub that, this will give me our angle. And I could sub that into h of theta, which will give me my height. So overall, it's going to look like, Then you sub that, h of theta 1. So sub that into that, and we should get our height. Easy. So let's do that. Using our cast. So we are going to do basically, this here is our x on t basically. So if I like sub in So that's theta on t, so x on 1 if I say. That's what we want to find out, which is this here. That's the, angle. And now subbing that to our h of, so the height in terms of that, we get, basically, this is our height. Beautiful. And we want it to 2 decimal places, so this here over here. So let's write that down. So we found that theta 1 is negative 0.2207. And subbing it in here, we got to 2 decimal places, 1.01 meters. Beautiful. So 1.01 meters. That is your angle. Done. All right, no mistakes here. Looks good. So this next question, state the rule for the composite function of h theta on t. That's easy. So we want to find h theta on t. So we can actually do this by CAS. Just go on your CAS. It's just a composite function. So we're basically doing h of x on t. Because, this is theta, then h of theta. Don't do that. H of x on t, basically. And enter. And this is your formula. That's your composite function. So let's write that down. I want to write it nicely. So it's basically like 3 on 2. I'm going to take the half outside. So minus half cosine, basically pi on 3 cos 9t over 2. And then close those brackets. Have I made any mistake? Half cos. Have I not rewrote? Beautifully. It actually looks good. No mistakes. Beautiful. That is it. So that is that equation. So let's highlight that. That's quite nice and easy. Next question. Let's do the next question. So, find correct to 2 decimal places the average height of the mass in meters. Beautiful. What an easy question. So remember, we're trying to find the average value. So the average value of this, which is basically, remember the formula? So we need, this is the formula for the average value. So like this, in this case, it's the height, the average height. So average is basically 1 over b minus a. This is a function. So like, a to b, f of x dx. That's your formula. So for example, this one here, the height is, because we have to use the height formula. So h on theta, d theta. Well, what are the theta angles here? Oh, before even doing that, sorry. I have to also 1 minus BA. So I need to find what's A and B. They gave us domain. Yep. So this is our A and this is our B. So what's B minus A first? So pi on 3 minus negative pi on 3, which would be just pi on 3, which is 2 pi on 3. And so if you're going to divide it by 1, so 1 divided by 2 pi, it's going to be 3 over 2 pi. So let's go down here. So it's going to be 3 over 2 pi. Beautiful. And that is our formula. So 3 over 2 pi, and we were going from negative pi on 3 to pi on 3. Those are our terminals, yep. Negative pi on 3, 2 pi on 3. I don't want to make simple mistakes. So yep, negative pi on 3 to 2 pi on 3. So h of theta d theta. Beautiful. Let's check what that gives us. So we want to 2 decimal places. Okay. So we said 3 over 2 pi times the integral from negative pi on 3 to pi on 3. H of basically x. Oh, let's call it h of x because x is already defined. So let's say a is our angle. So yep, dA. Enter. Control enter to 2 decimal places. We get 1.09. So 1.09 meters. That's your average. So 1.09. Beautiful. That's your answer. Hope that's correct. And that is it for this question. We are done. So now we're up to question 3. Not a bad question. So question 1 and 2 were quite nice. So quite happy with those. Next question. A small business has 4 people working full time. The business rents an office. And on most days, some people work from home. On any given workday, the number of people working in the office can be modeled by the discrete random variable n with the following probability distribution. Okay, so basically it's like the number of people that are working in a given day. So let's say in a day, we can have the probability of 2 people working there, like at that office is 0.4. And yep, and it's out of 4 people. So that if 2 people are working in the office, the other 2 are working online, for example. But you can see that there always has to be someone that's working in the office. It's not like, n equals 0. That's good to know. So find e to the n. So the expected value for the number of people working in the office. Easy, let's do that. So remember how to find the expected value of a probability distribution table? It's so easy because you know what it is? It's just multiplying n by the probabilities, plusing them. 2 times 0.4 plus 3 times 0.2 plus 4 times 0.1. That is the rhythm. So it's you multiply the n by their probabilities, their respective probabilities. So e to the n, it's basically going to be like 1 times 0.3 plus 2 times 0.4 plus 3 times 0.2 plus 4 times 0.1. Oops. Beautiful. And so putting that, what should that give me? Let's do a cat. That should give me 1 times 0.3, 0.3 plus 2 times 0.4, so 2 times 0.4 plus 3 times 0.2 plus 4 times 0.1. And time we get 21 over 10. So that's your answer, 21 over 10. Beautiful. That's your expected value. Next part. Find the probability that all 4 people are working in a given in the office. Given. So given is conditional probability that at least 2 people are working in the office. Easy. So let's write that down. So we want to first find out the probability that all 4 people are working in the office. So all 4. So the probability that x equals 4 basically. So 4. N equals 4. So it's in terms of n. Given that at least 2 people are working. So at least, so basically n is greater or equal to 2. Done. So that's what we want to basically calculate. So using our conditional probability formula, we simplify this to be n is equal to 4 intersection n is greater or equal to 2, all being divided by the probability that n is greater or equal to 2. So I'm just going to, for some reason, it's only 1 mark, so I'm just going to drop that out. That's all I need. And I'm going to try to simplify that. So to simplify the top part, the intersection point, we just need to draw like a nice timeline. So imagine this is 2 and this is 4. So 2 is basically like a closed circle going forever to the right, because it's greater, and 4 is just a point. When do they intersect? They just intersect at x equals 4. So that it just basically is simplified to this. Probably that. N equals 4, sorry. All being divided by probability that n is going to be greater or equal to 2. Done. So we've basically simplified it to the most simplest form, and now we just basically put what we know. So when is n equal to 4? What's the probability? Isn't it 0.1? Easy. Divided by, what's the probability that n is greater or equal to 2? So we want to find this here. Isn't that easy? Because isn't it just 1 minus 0.3? Because you know how easy it's, you can add these up, but let's say the quickest way is if this is left out, it's just going to be this like 1 minus 0.3 to get the overall probabilities of the other ones. So which is 0.7, which is 1 on 7. That is your probability. Not too bad. Next question. Let me just change the highlighter color. Okay, let's do it. Next question. In a fortnight with 10 work days, we have 10 work days. Find the probability that all 4 people are working in the office on at least 3 days. At least 3 days. Write your answer correct to 4 decimal places. This is binomial. They've now given you n, the number of work days, and they've also given you the probability of success, which is working for 4. We have 4 people working in that office, and we want it to be at least 3 days. Easy. So we're going to let basically x be binomially distributed, where x is basically the number of days out of those 10 work days, where 4 people are working. So the probability that is binomial, where n is what's the number of work days? 10. What's the probability of success that 4 people are working? We said that was 0.1 from here. So 0.1. All right, and we want to find the probability. So probability that all 4 people are working in the office on at least 3 days. At least. So basically, x is greater or equal to 3. And so we can calculate that using our CAS. So this here is a binomial CDF. Let's go. So menu, probability, distributions, going to binomial CDF. So what's the number of trials? We said it was 10. What's the probability of success? It's 0.1. What's the lowest bound? It's 3, and we go to the maximum upper bound, which is 10. You press OK, and this is your answer. So we want it to 4 decimal places, which is 0.0702. So let's write that down. So 0.0702. Beautiful. Nice. So let's highlight that. Perfect. Yeah, that is it. Next question. D. The business owner is trying to find ways to reduce costs. Her daily electricity costs in dollars can be modeled using a continuous random variable C, which has the probability density function. All right, nice. This looks good. Identify the maximum daily electricity cost in dollars for this small business. Easy, isn't it just 10? Because C is the cost. Yeah, C is the cost. And we want the maximum. So the maximum daily electricity cost, isn't it just 10? The lowest is 0. But the highest is 10. So the maximum is actually $10. That's a nice, easy part. So it is $10. All right. That was an easy one marker. Now, next question. Find the mean daily electricity cost in dollars. So we want the mean, the average value, the expected value. That's easy. So remember how to calculate that for a probability density function. It's just basically, so let's say f of C is that. So you just have to basically integrate it. So to find the mean of C, you integrate from 0 to 10, and you basically multiply C times f of C, dc. So can you see how f of C is your, basically this function? You have to multiply by C to get the expected value. The function, you need to multiply by C. Yep, and it's equal to what? And that's going to give you your expected value. So let's do that. So first I'm going to define what actual f of C is. F of C. And it's basically, wow, it's 3C times C minus 10 squared, all being divided by 2,500. So, and we want to integrate, so 0 to 10, C times f of C, dc. Enter. So $4. So let's put that down. So basically the mean, so the average there, the cost is $4. Done. Not bad. Next question. Find the probability that on a given day, the electricity cost is within 2 standard deviation of the mean. So you should already realize, wait, 2 standard deviations from the mean. So basically what we're trying to find is the probability, basically where, let's say, you know, this is C in this case, where it's between mean minus 2 standard deviations and mean plus 2 standard deviation. This is what we mean by 2 standard deviations from the mean. You should realize that, wait, isn't this here, this expression, approximately close to 0.95? Yes, so our answer should be around 0.95. Of course, we want to get the exact value, which we can, but yeah, it should be around that 0.95 mark. So we want to find this probability. Now, to do that, how do we do it? Well, we need to know the mean, and we do actually know the mean, it's 4, but we need to get the standard deviation. How do we get the standard deviation? We need to get the variance. So let's do it here at the bottom. So to get the variance of C, what we're going to need is, remember, you need the expected value of C squared in this case. C squared minus the expected value of C, all being squared. Now to get the expected value of C squared, how do we do that? Well, to get that, we have to do is this. We have to integrate it from 0 to 10. Was it from 0 to 10? Yep, 0 to 10. You know how when we find the expected value, you know how there's 1C, you multiply like by 1C, f of x? We're f of C, dc. In this case, we have C squared, so we have to multiply by C squared. So that here will give me that, basically expected value of C squared. So let's do that, and I'll cast. So just copy this, and put a squared there. Done, 20. So let's write that down, 20. Now we've got that, easy, let's rub this out. So we got 20. So 20 minus your expected value squared. So your expected value is what? We got 4, which is squared, is 16, which is going to give you 4. Their variance is 4. Done. Now remember, your standard deviation is what? Isn't it just basically the square root of your variance? So square root of 4 is your 2. Done. We found our standard deviation, which is 2. So let's get this first here. So it's the mean, which is your mean is 4, minus 2 times your standard deviation, which is 2. So 4 minus 4, basically, which is 0. So it simplifies to basically 0. Let's all equal to C. Let's all equal. So, and the next one is mean plus 2 times your standard deviation, which is 4 plus 4, which is 8. Done. That is what we basically wanted to calculate. And now that is equal to what? So you remember, it's just the integral from 0 to 8 of f of c dc. That should give you the probability. So let's go back to our CAS and take this and just get rid of this. From 0 to 8. Enter. And it gives you that. Now, we don't want it, the question doesn't say in decimal, so we just leave it as the exact value. So let's write that down. 608, all being divided by 625. Beautiful. Now, let's go back to the CAS. Let's go back to the CAS. Now, if I press Control Enter, it should be approximately around 0.95. That's what that expression should be around. Yes, it is. It's a little closely, but it's a little bit far off. But it is quite close to that 0.95 mark. So perfect. That looks correct. So let's go back to our paper and finish off the questions. This question here, let's have a try at this. Okay. So the business owner plans to reduce electricity costs by installing LED sensors. She researches an LED sensor manufacturer and finishes the following information. She finds this following information, In a random sample of 200 LED sensors, 30 LED sensors were found to be defective. State the sample proportion of LED sensors that were found to be defective. What a beautiful question. Easy. So we know that the sample proportion is what? Isn't it just the formula x over n? So our x is how many? Like LED sensors, which is 30, divided by our n, the total, which is the sample in 200, which is basically 3 on 20. Easy. So let's highlight that. That was your sample proportion. Next one. Using the sample proportion to find a 90% confidence interval for the population proportion of defective LED sensors corrected to 3 decimal places. What a beautiful, easy question. When I see these kind of confidence interval questions, they are so easy because you can just do them in your CAS. So let's go to our CAS. Now, it's only 1 mark, so let's do it quickly. You just basically go to menu, you go to statistics. You go to confidence intervals, and you basically go to 1 prob C interval. So now you have successes. What is the successes? You remember our successes was 30. And the total of those, out of the total, over sensors were 200. So 30 were defective out of those 200. And the C level is what's the confidence level? Remember, we're finding 90% confidence. So make sure it's 0.9. Press OK. Control Enter, and this gives you all the information that you need. It gives you your C lower, your C upper. It gives you your P hat, your actual sample proportion, what we just got basically, your margin of error, and your N value, which is just 200, of course. So let's write these down here. 2, how many decimal places? 3 decimal places. So your confidence interval is going to be basically 0.108, comma 0.192. Is that right? Have I made any decimal mistakes here? 0.192. Beautiful. Looks good. That's that one. Next question. F. A new sample of size n is taken, which is used to calculate a 95% confidence interval for the population proportion of defective LED sensors. This confidence interval correct to 3 decimal places is given here. So this is the actual confidence interval. Using the value z equals 1.96, determine the sample size n. This is actually quite easy, especially it's an exam 2. What you can do is you can make 2 simultaneous equations. So write the formula for confidence interval. Let's write that down. So it's basically p hat minus z. Now z is 1.96. They've actually given us here 1.96 times the square root of p hat 1 minus p hat, all being divided by n, the total, comma, and we do the same, plus 1.96, all being divided by p hat, times 1 minus p hat over n. Beautiful. So this is our confidence interval formula. Now, we're trying to find 2 variables. Now, of course, 1 variable, which is n, but we can easily find 2 variables because we got 2 values. We can make 2 simultaneous equations. So, putting this in our formula. So this equation here, this equation equates to that 0.062. Let's do that. So I'm just going to rub this out, and move them here. So move this one here. This one here equates to that 0.062, and this one equates to 0.213. And so we can now calculate n, and we'll also get n and p. So So let's go to our calculator and we can do this using our calculator, using our simultaneous linear equation. So let's do that. So get a menu, go to algebra, and go to solve systems of equations. And we're going to, basically, we're solving for P and N. And we have, of course, two equations. Okay? Why is it not? So P and N. Okay. So let's start the first one, which was P minus 1.96 times the square root of P times 1 minus P over N should equal to, we said was 0.062. I'm basically copying this whole thing here. And just make this plus for the other one equals what? 0.213. And press enter. Oh, did I make, yep, 0.062, 0.213, everything looks good. These are their values. So if you press Control Enter, oops, syntax error. Let me get that real. Control Enter, these are your values. So you're probably a success and your N value. Now, of course, the N value has to be an integer. It's the number of something. It's integer. So it's to round that up, it's basically N equals 80. Hope that makes sense. So that was quite easy. N equals 80 basically. All right, done. And we have done that question, so we've done probability. I'm so happy. So let's do question 4 now of the new question. So let's just change color. We'll keep the same color. Timothy has created a tiling pattern using transformations of the cubic function this. So from -4 to 0, f of x, and we don't know what these are. So we have two, so a, b, and c, where a and b, c are element of all reals. On the graph below, the function f is shown in bold. So it's here, right over here. It's this bold equation. If you can't see it right through my screen, so it's this bold. There it is. Here it is. So on the graph below, the function f is shown in bold. The rest of Timothy's tiling pattern is shown with dashed lines, which are images of the transformation of f. So basically, images means the transformed version. So if you transform this here has been transformed so many ways to make all these tilings. Next question. A, the translation of f given by f2 of x, so this is your new translation, is f of x, x minus 4, so it's been translated 4 units to the right and 4 units down, describes a different edge of one of the tiles. Trace over the edge of described by f of 2 on the graph in figure 1 and label this edge as f2. What an easy question. So this is your f basically. This is your original. This is your f. You can see that this is your f. What's happened is it was translated what? 4 units to the right and 4 units down. Okay, let's think about it. You take this here, translate it 4 units to the right. Oops, 4 units to the right, like that, and then 4 units down, like that. It is this one. Perfect. So right here, jackpot. So this here is your f of, what was it? F of 2. So labeling it. Done. Yep. Trace over the edge described by f of 2 on the edge and label this edge. Beautiful. Easy question. Next question. Given that f has a stationary point on the inflection -2 to 2, so this makes sense, yep. And an axle intercept at 0, 4, yep, we can see that, 0, 4, okay. Find the values of A and B and C. Quite easy. There's so many ways you can do this question. You can already determine the equation because remember, if you know the inflection point, and this is given in this formula, we know that B has to be negative, basically 2, because when you're writing it, it's going to be x plus 2 cubed. And remember, this here, meaning that it's the original graph is translated 2 units to the left, which is what we have here. And what about and it was also translated up 2 units, so plus 2, but we don't know A. And to find A, we actually sub in that -4. So that's how the equations are going to look like. And and you basically, for example, you sub in that that 0, 4, this one over here, this point, and you should get your answer. Now I'm just going to do this all by hand, all by like calculator. There's a much quicker way if you want to do that. So that's quicker, actually. That's much quicker. But I just want to show you how I would, like, if there's another step to do it. It's quite, much also easy. So is that, okay. So we need to find 3 values for A, B, and C. We need 3 points. We need 3 features of the graph. Luckily, we have already 2. These 2 lie on the graph, yeah? So let's write these 2 equations. We have f of -2 equals 2. F of 0 equals 4. And because this is a stationary point inflection, when you derive it and sub -2, it should be equal to 0 because it's a point of inflection. So basically when f dash, so f dash of -2, when you sub a negative, it should be 0 if it's a stationary point inflection. So you've got 4 equations and 4 equations for 4 variables. This you can calculate using your simultaneous linear equations. Let's do that right now in my class. So I'm going to just define f of x right now. So f of x is, control n, just make a new, f of x is a times x minus b to the power of 3 plus c. Done. So what we said, so go to menu, go to algebra, go to solve systems of equations, and we have 3 variables, so a, b, and c, and we want 3 equations. We have 3 equations. Press OK. Why does it change? A, b, and c. Why? Okay, so the first one is, if I go down, so what did we say? We said that f of negative 2 is going to be equal to 2. Next one we said was f of 0 is going to be equal to 4. The next one we said was f dash, so the derivative of f of x, where is going to be equal to 0 when x is equal to negative 2. Enter, and we got all our values. A is 1 over 4, b equals negative 2, and c equals 2. Done. How easy. We already know b and c were correct, so you just had to, So let's write that down. So your a is going to be 1 over 4. Your b is going to be negative 2. And your c is going to be 2. Done. That should give you that mark. Next question. Okay, so C. So we tried this here. So it says, the piecewise function P is continuous where the first component where the first component is f and the other component is a translation of f, and both are edges in Timothy's tiling pattern. Complete a possible rule and domain for the second piece of piecewise function. So we have f of x, and basically what we need to know is that P is continuous. So and it's basically f, but it's only translated, and it's the edges of the tiling pattern. Let's have a look here. So what it's basically saying is, like, you know how this is f here, right over here. This one f. So you know how tile looks like this. These are the tiling pattern, and that also here, that one, that's like a tile. Now basically what we need to do is it has to be continuous. Now it is continuous like here. For f, you know what, continuous for this one, continuous for that one, continuous for that one, continuous for that one, continuous for that one. So there's so many, in terms of f, it could be continuous for all of these values, but they told us it has to be translated. That's the hint. So, having a look at this, if you have your f here, and it can only be translated because they told you that it was a component that is a translation of f on both edges in Timothy's tiling pattern, what would happen? It cannot be this one over here. Why not? It's because even if you translate it, let's say, you might think, translate it 2 units to the right. Okay, you translate it 4 units to the right. What's going to look like? It's going to look like this. It doesn't look like that. And you can reflect it. So it's just like, in other words, this f, you can't actually get this. So reject this. What about this one over here then? Also the same, if you translate it down by 4 units, you'll get this. And it's not the same as that. Imagine like you can translate it right, left, and stuff. What about this one? Ooh, this one looks good. Yeah, you can translate it basically like, 4 units to the right, so it'll be like there. And then 4 units down. Yeah, but there's a big also problem. It is not going to be continuous. They're not connected to f. It's not connected to f. So the only possibilities are these two graphs. This one here and this one here. These are continuous of the graph. And these are possible, actually. Because this one here is just translated 4 units to the right, and 4 units up. You get that one. You translate, 4 units to the left, 4 units down. You get that one. So these are 2 possibilities. I think that, these are the 2 possibilities that you can basically get. And we didn't write the piecewise function. So I'm just going to write I'm going to write both of them, but you have to just choose one. So I'm going to try to write this one here. So it is basically just, f translated how many units? So 4 units, so it goes 2, 2. So 4 units to the right. So let's do that. F is x minus 4. So translated 4 units to the right. And how much units to up? So if it's here, translated 4 units up. So you're going to plus 4. All right. So we've got that. Okay, x minus 4, x plus 4. That looks good. And we also have to write the domain. Now, what's the domain of it? Here. We can see it's from 0 to 4. So 0, less or equal to x, less or equal to 4. Now be careful, don't write less or equal to 0. Write it less, because it's already equal here. Because if they're continuous and already this one's equal to it, make sure this is not equal to it. Because you know how they are continuous? Yeah. Beautiful. So it's going to be basically, so negative, 0, less, because we don't want to equal, because this one's already equal to it. Less than x, less or equal to 4. Is that right? Don't want to, any basic mistakes if I see, so yeah. Less or equal to 4. Done. Let's draw the other case. Well, the other case is, of course, just translating how many? 4 units left and 4 units down. So it'll be basically f of x plus 4. So 4 units left and 4 units down. And the domain would be, it will be basically this. So it'll be -8 to 4. -4. -8 less or equal to x less or equal to -4. Now make sure, again, like what we said, make sure, so -4. -4 is already included. So make sure this is just going to be less, not equal to. Less. That's it. So that is the other rearrangement you can get. So any of these, you get the answer. These are possible values you can get. I hope that kind of makes sense. If I'm not understanding the question probably, but yeah, that's what I'm thinking. That's how I interpreted the question. D, find the rule and the domain of the inverse function of f. This is so easy. You can do this with the CAS so quickly because it's 2 marks. You need to kind of show some working out. So what we just have to say is I'm going to do it by hand now, and then I'll do it also by CAS, quicker. So what we just need to do is basically let f of x equal y, and swap x and y. That's what you need to say in the statement. And now let's do it. So basically it's going to be x equals, so swapping, okay, so it's, let me write f of x, the function. So f of x is what? 1/4 x plus 2 cubed plus 2. I think that's the equation. Let me just double check that. So translated, yep, so x plus 2. And plus 2. Beautiful, that is that equation. So this, you swap, this becomes your x, basically. And this becomes your y. Done. And so we solve for y now. So it's going to be, basically, this will become, you minus 2 on both sides, times on both sides by 4, and you're left with y minus 2 cubed. Cube root both sides, so you basically get cube root 4x minus 2 is equal to y minus 2. And so hence y is going to be equal to cube root 4x minus 2, plus 2. Done. So overall inverse function of x is going to be 3 cube root 4x minus 2 plus 2. Done. So that is your inverse. You just have to show some of the work, and you just need to find the domain now. So you've got this function. The domain, remember, how do you find the domain of the inverse? It's so easy because the domain of the inverse is the same as the range of the original function. So your domain, let's say the inverse, is going to be equal to the domain, the range of the original function. So we just need to find the range of the original function, which is what? Well, quite easily, it's this. Let me just take this out. If this is our original function, it's from 0 to 4. That's the range, so 0 to 4, and it's included. So, I want to just write a nice statement, overall statement. So I don't want to kind of waffle too much, so I'm just going to write it as f of -1. So the domain of it, which is, we said from 0 to, so 0 to 4, goes to all reals, and so your function is that 4x minus 2 plus 2. Done. That is it. That here should give you that mark. So you've got the domain and you've got the inverse function, and you basically showed some working out. So that is it. Now, how do you do this by CAS? How can you do this so quickly with the CAS? Like, if it was 1 mark, straight away do it by CAS. Don't waste your time with this. I'm not gonna lie. I want to show it by hand just so you can guys understand how to do the question really visually. Because you need to know how to do it by hand also. And so yeah, this is how you do it. Let's do it by CAS. How do you get that function? How do you get that inverse function so quickly? This is what you just do. You basically just define, of course, define f of x. So let's define f of x with these new stuff. So f of x is that now. So basically, to find the inverse, all you need to say is solve f of y equals x comma y. This here, we'll press enter. This is your inverse. This is your inverse function. So this is the same as what we did, but this is like a little bit in more surds. Still the same function. So you could put this or what I did, still you'll get the mark. And you just need to write also the domain of that. And you'll get the full marks, which is 0 to 4. How easy was that? So quick. So yeah, nice question. Okay, E. Let's have a try E. Let m and n basically be an element of all reals. And g of x be m times your... So m is basically like a dilation by factor of m parallel to the y-axis times by your inverse. And this is here is a dilation by factor of 1 over n parallel to the x-axis, be a function describing a transformation of the inverse of f. Okay. So we've got, okay. So g of x is basically those, it's m times that of the inverse, be a function describing a transformation of the inverse. Okay, find the values of m and n, given that g of x describes the edge joining -4, 0 and 0, -4, shown in the bold in figure 2. Ah, there it is. There it is. So we would place, so was it -4, 0? Yep, -4, 0, and this here. So this is what we basically want to, this is what overall our g of x function is. All right. How do we get that? Well, that's quite easy. Let's think about it. So first, the inverse. Your inverse of f of x is what? Remember, it's just basically swapped. So this is, okay, imagine this is your right now your original. So remember your inverse, what happens is they swap. It gets reflected along the y equals the x line. So it will become here, and it'll become here, and it'll actually look like, so if I reflect that, it will look like this. There it is. It'll look like that. And so, okay, so it's, that's your inverse basically now. That's your inverse of f of x. And wait, so g of x, isn't it just you reflect it to get g of x, overall this, function? Isn't it just you reflect it along the line y equals line? So you just basically say f of -1, -x, so you reflect that along the y equals, the y equals line axis, and you get the function g. So that is it. That is your jackpot. So g of x is m times f of inverse of -n times x. So your m has to be 1, because, it's nothing's in front of it. Your m has to be 1, and your n has to be -1. Wow, that was actually much easier. And there's actually many ways you can do this. Like, I was thinking of another way too, but this was so much easier. So another way that I was going to do it is this. So you know how we found the inverse function? So inverse equation, I'll just write it down. Okay, D. So you know how we found this inverse equation? Right over here. Copy. Come here and paste them. You know how we find this inverse equation? Let me just, oops. So you know how we found this inverse equation? Well, what we can do is, because we know we have 2 points on it, don't we? Don't we have 2 points on it? So imagine, okay, so make this g of x, of course. So like, so if this is f of x, so do these transformations on it. So write it as like m times. So make sure like put m in front of it. So the whole function gets basically multiplied by m. So this whole function will get multiplied by m. And then you put n also in the middle of it to make it look like g of x, basically. So basically for all x values, it'll become, so that's x value, make it basically become n of x. Not kind of, oh, it's so ugly. There it is, n of x. So that, can you see how basically this is the transform version? So that's now g of x. So imagine this here is your g of x, basically. Now this is your g of x. Now all we want to solve is m and n, which are 2 variables. And don't we already have 2 points on the equation? -4, 0, -4. Let's sub these 2 points in, and you will get your actual m and n. How easy was that? So let's do it. So basically, g of x, so you know how this is your inverse, but a little bit written different. So this is, let's call it f1 of x. This is your inverse right now. Yep, on our cast. Remember how g of x is what? So g of x is what? So g of x is defined as, remember, it is m times f1 of x, so f1, which is your inverse, n times x. That's it. And now we sub in those 2 points. So go to menu, go to algebra, solve simple equations, and we have, of course, m and n. That's what we want to solve. 2 equations. Beautiful. So now it's the 2 points were g negative 4, 0. And g of 0, negative, basically negative 4. Enter. There it is. 2 values right there. How easy. So yeah, hope that makes sense. Now let's go back to this question. F. Find the area of one of the tiles. An example is shaded in figure 2. So we just basically want to find the area of one of these tiles. Let me just rub this out. Wow. Man, should we take this right here? Nah, don't we need it? I don't think we need it right now, so let's take it out. So we want to find the area of one of these tiles, this whole tile. How do we do that? It's easy because you know how we have the function f of x? If I find the area under it, by symmetry, isn't it just 4 of them? So like, for example, this is 1, and this is the another one of the same, but it's just a little bit moved, like, a little bit, so some, transformations that's happened to it. So it's the same thing. That's another one. Then we also have another one. We have 4 of the area under the graph of this. So for example, if this was, I don't know, let's say it was 2, the area under it was 2. It'll be 2 times 4, because these will be the same, which is 8. So we just need to find the area of this and multiply it by 4. I hope that makes sense. Okay, so area is 4 times the integral from, what is it, negative 4 to 0 of f of x dx. Which is, let's write that down now, Cass. 4 times the integral, negative 4 to 4. So negative 4 to 0, sorry, of f of x dx. Enter. 32. So that's your answer. So write 32 units squared. Done. Next question, G. Using the derivatives of f and g at x equals negative 4, show that the angle at the left corner of the shaded tile, so this shaded tile, why did I group it? Yep. So cut this. So left corner, so here, let me draw in a different color so you can see it. So left corner, so negative 4. So using the derivatives of f and g at x equals negative 4, show that the angle at the left corner of the shaded tile at the point negative 4, 0 is 90 degrees. Okay, so we basically want to show that this angle here, like, this here, is 90 degrees. Like, look, if you draw, like, 2 tangents here, nice 2 tangents, there should be, like, a 90-degree angle, and that's what we need to show. But that's quite easy. So we need to use derivative calculus. How do we do that? Well, let's think about it. Well, this is the way that I would do it. There's many ways, of course. What I would do is I would draw to find the equation, we'll find the gradient of this. So find the tangent of the gradient of the f of x at negative 4. And it will give me the gradient here. And I can use that using, tan theta equals m. I can use that to find the angle, this angle here, which is the x-axis to the line. Yep. And I'll do the same for this one over here, for the inverse, g. And I'll also find the tangent at x equals negative 4, which will look something like this, basically. Let me just move it a little bit like that. Like that. I'll do that, and also I'll get the angle using that same formula, and I'll get this angle over here. Now, if I add these angles, they should be adding up to 90 degrees. That will tell me that they are right angle, basically perpendicular to each other, right angle to each other. So that's what I'm going to basically do. So let's do that. So what I need to first do is I'm going to basically find the gradient. So f dash at negative 4 for f dash, and the same for d dash at negative 4. And these are going to give me, when we get this, we can, use those gradients to help us. So let's go to our calculator. And so we want to derive f of x at x equals negative 4. And that's going to give me 3. Beautiful. And we'll do that for g of x. Do I have g of x, please, defined? Do I have g of x defined? So it's in terms of m, but we already know m is 1. So we can get that out. Oops. M is 1. N is what? We said it was negative 1. So negative 1. So negative x. Done. So let's define this g of x here. Beautiful. So we said that, So derive it and find the derivative at -4, the gradient of the tangent at -4. And that's -1/3. So let's write those down. So this one was 3, and this is -1/3. You should straight away realize they, like, whoa, they fit the formula for perpendicular normal equation. So, you know, if you have two equations, so for example, you would straight away realize, like, you know, if you have, let's say, you know, you have a line here, and that's the gradient m. And let's say you have a gradient here, like another line, and they are perpendicular. We know that the perpendicular gradient is -1/m. And isn't that what this is? So you know how m is, in this case, 3. This one. If they are perpendicular, the gradient of the other one should be -1/3. And which it is in this case, can you see? So you can use that proof to kind of show it. But that's what I'm going to do. I'm going to try to show it in a much more complex way, just to show another way to do it. So, what am I doing? So cut. Okay, let's find the angle. Remember using your tan inverse of your gradient equals to theta. Doing that for both of these, we should get the angles. -1/3 theta. Let's do that. Go back to our cat. Tan inverse of 3. And now this is in radians. I'm just going to keep it in radians, to be honest. -1/3. There it is. These are your two. So let's write those down. So your theta for tan 3 is pi on 2 minus tan 1/3. Your theta for the other one is negative tan inverse 1/3. Done. So have a look at this. This is what I want to show. This is the angle. Let's call this angle 1. This is angle 2. This is angle 1 right now. This is the angle 1. This is angle 1. Beautiful. We have angle 1 and it's positive because it's above the x-axis. The thing with angle 2 is we don't add them. Make sure angle 2 is positive. You know, right now it's negative because it's below the x-axis. So we want to make sure it's positive. So right now, you know how it's negative here? Make it positive. And then if I add these two up, this should be like 90 degrees basically. This should be 90 degrees. So basically pi on 2. Pi on 2 is 90 degrees in radians. So if I add these up, so you know, theta is pi on 2 minus tan inverse 1/3 plus tan inverse 1/3. These cancel out. You can see that these cancel out. You're left with theta is pi on 2, and which is 90 degrees. Beautiful. That's another way you can prove it. I hope that helps you out. So, beautiful. Done. All right, sorry, I didn't highlight these. Did I not highlight anything else? Yep, so those, there it is. So they are 90 degrees. Many ways you can do that. So, hey, let's do H. All right, the family of functions divide by this. So g of x is justly translated where k is an element of all integers. So like -1, 0, 1, 2, 3. And so, okay, so like if I summon 1, it's basically translated 8 units. If I summon 2, it's translated 16 units. So this gives an infinite set of edges in Timothy's tiling pattern, 3 of which are shown in the bold. Ah, I see. So this is what's happening. This is it's like a general equation that basically gives us, so can you see this tile here? So basically it translates it every time 8 units. So can you see how it's here? If it's translated 8 units, it will be this one over here. Translated -4 units to the left, this way. So any value will always just translate right, left. So it's always going to give you this tile, like this tile basically. It's a general solution that gives you this part of the tile, the bottom left corner of the tile. Three more families of functions can be used to bound an infinite set of tiles centered on the x-axis, 3 which are shaded on figure 3. Complete the table to define 3 such families of functions in terms of given functions f or g and the parameter k. So basically what we need to do is, this one's already given to us. We need to make up 3 general equations. So one for this, so that makes up this repeating. Just repeating, it repeats. So like, a general, solution or equation that gives us always, this here translating basically right, left, and it's always, and it's always giving that infinite set of thing. And we have to do it for all of them. So we have to do it with this one too. And we also have to do it with this one too. We do it for all of them because this will make sure we get an infinite bound. So it will give us this. We can easily find this, Yeah, that's what we need to do. So a little bit is a difficult question, but it's not too bad. Let's just take it slowly. All right, so let's have a look at the yellow one first. The yellow one, let's try this one. The yellow one's just f of x. And what is the general solution? So f of x, like imagine, okay, we want basically, if we translate it 8 units, so yep, 4, 4. If we translate 8 units to the right, we get this. We translate 8 units again, it'll look the same. Yep, that's good. What about if we translate it 8 units to the left? Yep, perfect. So the general equation for the actual f of x is what? It's actually basically y equals, this one's easy, f of x minus 8k. So y, k is just an integer. Like for example, if I sub in k equals 0, it'll be f of x. Done. F of x is this point here. Beautiful. If I sub in 1, now look at that. It'll be f of x minus 8. Just double check them. So it's 8 units translated to the right, which looks like it's this one. What about if I, sub in the -1? F of, so if I sub in the negative, it'll be x plus 8. So it's basically this one over here. So you see how it's giving me this infinite, it's always giving me this infinite solutions, graphs of these. And that's what we want. So beautiful. That part is done. How great. So that is the general solution for that one. Now we have to do other ones. I don't know why I duplicated them. Sorry. Cut that out. Let's do a green color. Let's do the next one, which is this one over here. What about this one over here? What is the general solution for that? Now, the problem is f of x, it's so hard to get this to that. Why? Because even, like, you cannot reflect it. If you reflect it, it'll look like this. Let me just show you. If I reflect f of x, it's not actually part of f of x. Like, it'll look like this. And then you still don't get this. Like, what are you going to do? Then reflect it, let's say, along the, reflect it still in the x-axis. It won't help you. It just gives you this then. Like, it's not going to give you that. The only way we get that graph is actually through g of x. Isn't that g of x graph the same as that? Look at that. If I put it on top, it's actually the same. So guess what? It's just translating g of x to make that one. So we have to translate g of x to make this one over here. And what do we translate it? Well, it looks like we translate it 4 units up. So like g of, let's say, x plus 4. So 4 units up. So if I translate them always up, 4 units, so it'll go like that. And then always 4 units to the right. Let's double check that. So it'll be like x minus 4. X minus 4. Now that's for the first case, of course. What about the second case? Well, what about if I wanted, like, how we got that? What about this one over here? And then make up this one here. So because I want to make like a general. I need to have that k value, like a value of k that gives me this infinite solution. So that plus 4 is always there, by the way, because it's good to always push it up and then just always translate it. So the next case is if I do that, I need to translate it from 12 units. 12 units. Okay, so translate it 12 units. So it means that, okay, I have to translate 12 units. So we went from g of x minus 12 plus 4. That's your second part. What about we do this one also? Because I just want to find this general equation, like solution. What's that, like, equation that's coming up? The next case, if I want this, it's basically just translating it like 2 units, always 4 units up, of course. So it's going to be g of, and how many units to the left? Just 2. So x plus 2 plus 4. So what is that general solution that's happening here? Is that right? So because if I take, no, what am I doing? Sorry. Oh my, I'm just over confused. Wait, I'm over confusing stuff. I'm over confusing stuff. All right. And this was actually quite hard because it's like mixing me up for some reason. So I'm basically getting the g of x and I'm trying to make it always the up one, the top one. So if I do the next one, so you have to just translate it 2 units to the left. So here, so like that. No, I have to translate it 4 units to the left. Oh my God. Nope, not 2 units, 4 units. So it's going to be plus 4. Plus 4? Yep, and then plus 4. Okay, this is the equation. So what's the general equation? What do you see? You see that? Here it's 4. Then you have to plus 8 on this to get it to -4. Then, like, think of it like -8. So like minus 8 from this. Always. You minus 8 from this, you get -4. And then you minus 8 again, you get -12. So it's going by -8. So actually, so the general solution could be like, basically like x plus 4 minus 8k plus 4. Could it be this one? Let's try. And we'll just rearrange it to see. So it looks like it's going through this sequence of that minus 8k. Let's try the first part. Is it this actually? So if I, let's take this out. So let's try the first case. So if I sub in 0, it'll be g of x plus 4 plus k plus 4, which is, 4 units to the, rubbish. Oh my god. It's going to be 4 units to the left. Make sure it's a minus. This is going to be a minus. Done. So that is a change that we must do. So what about if I sub in 0? It'll be negative 4 plus 4. Beautiful. So that's 4 units to the right. So you basically get this. 4 units to the right. Sorry, 4 units to the right. 4 units up. Done. What about the next one? If I put 1, so it'll be x minus 12k. Yep. So 12 units to the right, up 4 units. Okay, what about if I sub in the other case, which is negative 1 as k? It'll be basically, so negative 1, 8 minus 4, which is 4. So so it'll be translated 4 units to the left like that. Then up. Beautiful. We've got the general equation. It is this. Damn, it quite took too long. It's a little bit, It's ugly. It's very ugly. So that is for the green one. So so y equals g of x minus 4 minus 8k plus 4. I want to make sure this one looks good. Doesn't look too bad. So now next one. Let's do so that's going to give you that green one. Now what about the other case? So we want this one over here. How do we get this? Now, look at this. Isn't that just f of x translated? Look, isn't f of x translated like 4 units to the right and 4 units down? Yeah. So that's kind of the sequence that I'm seeing. So, and I want to find the general solution that will always give me these ones here, basically. So it's f of x, we said, already 4 units right and 4 units down. So I'm kind of seeing the sequence. Now, that negative 4 units down is always for all of them. So you always translate it. But what's the sequence? So for the other case, what happens? So it's, this f of x translated, 4 units down, but it's going to have to get translated 12 units to the right. So it actually looks like it has the same equation as g of x, this one. So could it actually be the inside the same as x minus 4 minus 8k minus 4? Let's just double check that. So if I sub in 0, yep, it'll give me x minus 4. What about if I sub in 1? X minus 12 plus 4, minus 4, yep. What about if I subbed in the other case, which is negative 1? So it'll be x plus 4 minus 4. So 4 units to the left, 4 units down. Let's check that. 4 units to the left and 4 units down. Yes, perfect. We've got that general equation. So for that one, it's y equals g of x minus 4 minus 8k minus 4. Beautiful. That looks good. That actually quite took long. I don't know why that took long. But yeah, that's 2 marks for that. Yeah, quite a little bit disgusting, but not too bad. I hope those are correct. 5, let's do, I think this is the last question. Yeah, it is the last question. Let's get this paper done, man. I'm quite tired. Let's do this. All right, question 5. So let f be this, where f of x is this function. Show that the rule and the domain of the inverse of f is that, and where x is the element from 0 to infinity, so the domain. Because it's a show question, we'll do it by hand, and then we'll do it by CAS to show you how to do it on also a CAS. So remember, we have to also let f of x equals 0, and we're going to swap x and y. So it'll be like x equals e negative ey. So it's going to be basically log e of x equals negative ey. And divide both sides by negative e, we get negative 1 over e log e of x equals y. So this is your equation of the inverse. Done. We've shown that. Now, remember, the domain is what? The domain for the inverse is the same as the range of the original. So we need to find the range of this. So it's quite easy. It's just, y equals 0 asymptote. It's just reflected along the y-axis graph. So we can see that the range is from 0 to infinity. And that's why it's 0 to infinity. There it is. So, all right. So what I'm going to do, yep. So that is going to give you that mark, showing that working out. And I'm just, to get the, I think the other mark, we're just going to say the domain, dom, of the inverse, same as the range of the original, which is equal to 0 to infinity. Beautiful. There it is. That's a show question done. Next question. B. The graphs of f and the inverse are shown below. Okay. Their unique intersection is 1 over e. So 1 over e is also labeled. All right. Find the exact area of the shaded region that is bounded by the graphs of f, the inverse, and the coordinate axis. So they've actually shaded it for us. We need to find this. Well, we're going to break it down. Like, for example, we can see that this function, f of x, the area from here, it's from 1 to e is that area, basically. It's under it. Whereas then, the function is going to be the inverse, and then the area under it. So it's going to look like this, basically. It's going to be the area is the integral from 0 to 1 over e, that's 1 over e, of the f of x, so originally f of x, dx, plus 1 over e to 1, the inverse of f of x, dx. And so this here should give you the exact area. Let's do it. So I'm going to just define them in my CAS. So I want to define those functions first. Let's go. So control N this whole thing and let's make up new stuff. F of x is so f of x is e to the negative e x. So e x like that. We put a times on that. So yep, so e times the negative ex. Beautiful. And all we want to basically find is the what we were finding out is this. So the integral from 0. Oh no, let's also find the inverse. We already found the inverse. Remember we were saying about how to find the inverse using a CAS? Easy, like what we just did. Solve f of y equals x comma y. Done. That's the same as the one that we just have, but it's a little bit written differently. But yeah, we're going to use that. That's our inverse. So what we say? We said that is 0 to 1 over e of f of x dx plus, copy this whole thing, but 1 over e is at the bottom, this one, to 1 of the inverse, which is that. You enter, that is your answer. Yeah, find the exact area, it says. Let's put that there. 2e minus 3 e negative 2 units squared. Done. Okay. Let's go to the next question. Question G. So G is the domain's all reals. G of x is e to the power of ax, where a is an element of all reals except 0. Consider the function g of 1 of x, which is e ax, where a is actually 1 over e. So we've got the a value. Find the equation of the tangent to the graph of y g of 1 of x at x equals e. What a easy. We just need to find it. It's only 1 mark, so let's use our CAS. So let's just graph g of x. Let's define g of x and g of 1 of x. So g of x is just the general solution, like the general equation, so a times x. But g1 of x is the actual equation where it has a is 1 over e. So exponential 1 over e. So 1 over e times x. Done. And so we basically now find the equation of tangent at x equals e. So go menu, calculus tangent line, g1 of x, comma x at comma 1, basically e, sorry, e. Enter, y equals x is your equation. So just write y equals x. Done. Next question. Sketch the graph of g1 and the inverse on the axis provided below. Label the equations of the asymptotes, the coordinates of the point of intersection between the two functions. Easy. And the way they've given the graph is so good, because when they give it in this kind of scale, you can actually graph over your CAS calculator. When they have these little boxes, it's so good to draw them, because you can, with a trick on your CAS, you can actually get always these questions right. So let's talk about it. So we're trying to graph of g of 1 and its inverse. I'm going to just teach you a quick trick. So you can graph on your CAS and you can make sure it's the same figures, the same scale as your paper, so you can actually just copy and paste it on your paper. That's what we're going to do. So, for example, what we need is some information from the, paper, from the scale here. What we have, we need to know what's the minimum value of the x. So the lowest, how we have, this is your y, x-axis. What's the smallest value? On the left, -4. Now, what's the maximum value of x? So the one on the right, the highest is 6. Then what's the, also we need to know the scale of x. The scale of x is basically each square. So basically like these, so each square here. What's the scale of it in terms of x? Isn't it basically 1? They all go by 1 in the x. So 1, 1, 1 by unit of 1. And we do that for y too. So minimum for y, the lowest for y is -4. Maximum for y is 6. And the scale for y is also going by 1. And this is what we're going to need. This is so good. Because what we can do now is come to our, CAS. And we can do this. So first of all, before I even do that, we have g1 of x basically here. I'm just going to find its inverse. So remember, because we're going to also solve g1 of y equals x, comma y. So this is its inverse. Let's graph these. So that's your inverse. Go here. That's your inverse here. You've also g1 of x. We're also going to graph. Oh, oops. Let's go down here. Done. We've got these here. Look, the scale's not nice. So what we're going to do, go to menu, go to Windows, and Windows settings. And what we just said, let's put them here. Your x minimum is, we said, -4. Your x maximum is 6. Your x scale is 1. Your y minimum is -4. Your y maximum is 6. And your scale y is 1. Okay, this is perfect. You can see that they are lined up perfectly. And make sure to make it even perfectly, you go to view and you go to grid and go to line grid. Now, basically, every square is the same as the square in your paper. And all you have to do is copy and paste every exact. So for example, the first one is, the square is 1 and the other one's 1. So these are like your, So I'm just going to basically try to copy it, scale this as every point on my paper. That's what I'm going to do. I hope that kind of helps you when you get this kind of questions. So let's do that. I'm just going to, So, what am I doing? So let me just cut these out. Cut. Let's go. So I can see that I'm going to try to first draw the, what do we call it? The original, so g of x. So g of x would, it looks, so it starts here at 1. I just want to basically, if I go to trace, I just want to graph trace it. All right. So let's actually graph trace the inverse first. So we know it's 1. So, okay. So if I like sub in 2, it's around 1.8. So 1.8 is around here. If I sub in 3, it's 3 point, so in 3 and 3, approximately 3 and 3. So around here. There it is. If I sub in 4, 4.3, so 3.7, so 3.7 is around here. And if I sub in like 5, look, I'm just kind of nicely subbing, basically 4.37, so 5 is 4.37, so around here. And yeah, that's just a kind of a graph, and you know it's going to go like this, pass through these points, and you know it's going to nicely go, because there's an asymptote at x equals 0, of course. So it is a logarithm at x equals 0. And remember, there's also going to be for the exponential, it's going to be y equals 0. There it is. So y equals 0 asymptote. And so you just do the same for the other one. So I'm just going to do that same for this other one. So I'm going to just, again, go to, trace it. I'm going to trace everything. So I'm going to trace 1. We got 1.39. So 1 is 1.39, which is approximately here. So what about 2? 2 is 2, basically approximately 2. It's around here. What about 3? 3 is around 3. So around here, see, they're kind of intersecting there. What about 4? 4 is 4.36, so 4.36, which is around here. And then 5, 6.29, which is very large. So it's actually going like 6.29 is around here. So it would look like this, basically. And yep, like that. Done. So I've kind of drawn it in not the most nicest, but yeah, it does the job. So here it is. Perfect. So here's kind of, and you can see that they're intersecting here. They're intersecting somewhere there. Okay, so that's important stuff. So have we done everything? Sketch the graph of G1 and its inverse on the x-axis provided below. Label the asymptotes, yep, and its coordinates of the point of intersection. We just need to find the point of intersection. Let's do that. Go back to our CAS. So to find the point of intersection, what is it? It's basically, this is your inverse equals your, your original function. You solve answer comma x, which is What? Just 2 point, it's the same thing. And 2.71 is just E. It's the constant E. Why did it not just say E for me? Yeah. So it's E, and of course the Y value is going to be also E. Because it's in its inverse, so it crosses the line Y equals X. So look, if I do that, also the Y value is, oh, why is it, oh, sorry, X equals. Okay, why is it making my life, yep, also E, 2.7. So it's EE, basically EE. That is your point of intersection. That's a pain. Wow. Didn't draw it nicely, or not the most nicest, but yeah, I hope that helps you. It's very, yeah, that's all we need for 3 marks. Question D. Let's have a try this. Now, let A equal -4. And consider G of 2 of X now. This is a new function, so e to the -4x. Find the rule of the inverse of function G of 2. It's only 1 mark. Let's do it by CAS. So let's define G2 of X as, what is it? E -4x. And so we're going to basically, remember, solve G2 of Y equals X, equals X comma Y. So that here is your inverse. So let's write that down. So G2 of X, so basically -1/4 log E of X. Oops. Log E of X. So this here is your equation. Done. Yeah. So for 1 mark. Next question. Find the values of X where G of 2 intersects with its inverse corrected 3 decimal places. So we're saying values. Easy. So let's do our CAS. So go back to our CAS. It's basically when its inverse intersects our original function. So G2 of X, which is that. So we solve answer, comma, X, which gives me, wow, all these values. Oh, it's only 3. So yep, values, it says only the X value, so to what? 3 decimal places. So 0.028, and this one, that one. Let's write those down. So X is going to be, the first one is 0.028, so to 3 decimal places. X equals 0.301. X equals 0.894. Is that all of them? Have I made sure that the decimals are right? So X equals 0.8, X equals 0.31, 0.94. Yep, they look good. They look good. That's not bad. Beautiful. Next question, E. I think this is the last one. Wow, I'm so tired. I'm not going to lie. I just want to get this paper done. 2 marks. Now, normally this is always supposed to be the hardest one. Let's have a try at it. Find the value of A determines, the value of A determines the number of intersection points of the graph of G and its inverse. Complete the following table by stating the values of A in each case. And so the number of points of intersections. So like, for example, for 2 points of intersection, they've already given it to us. The A has to be between 0 to 1 over E. 1 point of intersection is basically, we need to find those. 0 point of intersection, what values of A? Yep, and 3. So let's do first, the first case, which is the number of point of intersection where there's no intersection, so there's 0. What values of A does that, like, you know, what's that values of A for that? Alright, so what I'm going to do for this one is what am I supposed to do here? I have to go back to the original equation. So I'm going to control N everything right now. Delete everything. And I'm going to just redefine G of X. Originally, what was G of X? I've got to go up again. Where I was. Wait. Yep, G of X, which is basically A times X. And so it's, what am I doing? And it's inverse. So inverse, remember, it's just basically solve, answer, so solve G of Y equals X comma Y. So this is its inverse, so let's graph these two. And let's put a slider so we can play around with the A values here. There it is. We got these two beautiful 2 functions, and we can play with the A values. Look, we can play around these A values and see. Now, the first one, going down, you remember, okay, let's just have a look at the first number of points of intersection for when they've already given us number 2. So I just want to have a look how it looks. So for 2 intersections, it said it's between 0 to 1 over E. So if I want to double check if that's 0, 1 over E. I want to have a look at that. And so if I play around these values, okay, so zoom out a little bit. All right, here it is. So if I play around this, you can see that they're always there's always 2. And they go up, you go up. Zoom a little bit out. Here it is. So look, you go up, it becomes smaller. You get larger and larger and larger. But if you approach 0, sorry, if you get smaller and smaller, so you become like, it becomes like this asymptotic behavior here. But as it gets larger and larger, close to 1 over e, it reaches, I think, so at 1 over e, it basically intersects once then, because it'll look like this. There it is. So it will intersect that once, and that's why it's not equal to that. So there it is. It's all equal. Yeah. So at basically 1 over e, when it's equal to 1 over e, let's just say this. So 1 over e, so I'm just going to say 1 point of intersection already at, you know, so a equals 1 over e. 1 over e. Please don't, oh, it has to do this rubbish because this is already defined. Let's call it a dot, no, a1. I'm just going to call it a1. So a has to be like 1 over e. So that's already 1 point of intersection. So that's a great way. Now, let's see, what about if it goes more than 1 over e? What does it look like then? So if that's 1 over e here, 1 over e, you just have to play around with it. Just play with the values and you'll actually realize the pattern. And yeah, we just make the values up. That's what you just basically do with these. Oh, sorry. Let's say that's 2. That's 1 over e. There it is. So go more than 1 over e. It just separates. There is no point of intersection. Yeah, so if you go like, let's say to 3, 4, or let's say 10, it becomes just like this thing and they never intersect. Just get closer. Yeah, they just become this straight line, like these straight, like asymptotic behavior here. So yeah, they never actually cross when they go more than 1 over e. So, alright, let's write that. 0 point. So I'm just going to write this here. So we're going on to intersection when a is greater or greater, not equal. Remember, not greater. But when it's equal, it's 1 point of intersection. We said here. Yep, 1 over e. Done. So that's also another way we've I'm just breaking everything apart. So when we come here, we can sort of put all the information all together and make up the equations. Okay. So okay, that makes sense. So what about? So we said 0 to 1. What about less than 0? Because you know how it's a was between 0 and 1 over e. What about we said now a little bit less? So what about if I say like, you know, -1, and so this one here 0. What is the values here now? So there's always, so from wait. If I go like 0.001 or something like very close to 0, yep. You can see that then it's just always 1 point of intersection, 1 point of intersection, 1 point of intersection. Yeah, 1 point of intersection. The more you go down, let's see, that's -2. Yep, still 1 point of intersection, 1 point of intersection. Then look at that. It's gonna cross 3 times then. It looks like it's crossing. If I go zoom in here, I see something here. Look at that. It's crossing once, but if you go more, let's say, I don't know, let's say -4. You go more, then it crosses 3 times. So you can look at these point of intersections here. 1, 2, and 3. Look, it's 3 point of inter. 1 there, and 2 there, and 3. So basically, what is it? What is the rule here? So what was the value when they kind of crossed like once here? Was it -2 point? So was it e? Basically -e in other words. Is that right? Because it said 2 point something. It was close to that value. Yes, it is. It's e. So, and if I go more than e, like some small value more, what happens now? Should get more than. There it is. You get more, so 3 then. So it is actually e, so -e. So wait, if I say -e here, so if I say -e to 0, yeah, if I say -e to 0, and then play around that, so is that going to give me always, what is it? So it always gives me 1, 1, 1, 1, 1, 1, 1, until I reach negative, basically, -e, which it can be equal to it, and that's the last point of one intersection. So let's write that down. So you know how we said 1 point of intersection? So why did I, no, this one here, it's, what, this is 0, by the way. Why did I, yeah, 0 point of intersection. This is 1 point of intersection. So we said, what am I doing here? What am I doing? Not that. So 0 point of intersection is that. 1 point of intersection, we said it was equal, and also we're saying now, what? It's between, e, -e, we said -e, less or equal, because it can be equal, to A, so A1 I'm going to call it, less than 0, not equal to 0. So these values also give us that. And so if we go more than that, like, you know, negative E, so like let's say negative 4, what happens? We always got 3 solutions after that. So if that was negative E. After that, yep, we got 3 solutions. And if we go like negative 10 or negative 20, yep, just 3 solutions. If you kind of zoom in there, it's a little bit getting more. Looks like it's, yep, there it is. So 3 solutions, 1, 2, and 3. So for 3 solutions, so 3 points of intersection. We got basically where A1, like the A value is basically, we said, is less than, and not equal, yeah? So less than E negative 1, negative E, we said negative E. That looks right. So that's the only thing I see that's really, yeah. We basically analyzed everything, so I think I'm going to write these down. So let's start with the 0 point of intersection. So we said for the 0 point, let's go back to our paper. So for our 0 point of intersection, we said basically that A was greater than 1 over E. So A was greater than 1 over E. That's right, so A is greater than 1 over E. So for 1 point of intersection, if I go down a little bit, we said that it was basically negative E, so it's included, to 0, not included, and union, the specific point, 1 over E. Don't forget this point, 1 over E also. And so we've already 2. What about 3? We said 3 was basically just A is less than negative E. Those are your answers. I hope those are correct. I won't be surprised if I made a little simple mistake here, but yeah, easy. I hope you guys enjoyed the video and learned something through it. Please make sure to like and subscribe for more future videos like this. I hope you kind of understood that it was not a bad paper. It's actually not a bad paper this year. I don't like the questions where you have to start making equations. Like that was, like these ones, it had a lot of those, which is, yeah, not nice, but not too bad, not overall bad. So yeah, I hope I took my time with you guys. Like, you know, overall, like, you kind of understood everything. I try to go as detailed as I can. And yeah, I hope you guys enjoyed this video. And please make sure to like and subscribe. And I'll see you next time. Bye-bye.